You know, I could dance like Michael J.
Okay, good day guys, we are back. So today is the first time we are going to attack an integral. If you look at the topic of or the title of this video, it said an integral consisting of the sine and the error function. We're looking at this, we don't have any error function, you can't see any error function here, but don't worry, it's very easy. Now, before we attack this integral, the first thing that should come to some people's head is that let me try if I can simplify this part. Yes, that is a very good point. We all remember that the error function, the definition of error function is this. We all remember, yes. Now, where t is just a dummy variable, that simply means this part of the question is simply the error function. Are we together? Very easy. So the integral is just simply equal to the integral from 0 to infinity, the error function evaluated at x minus 1 sine of x. Yes. Now, the next thing that should come to our head, I think, is that maybe we should open the brackets. But if we are to open the bracket, we would have sine x times the error function of x. And we also have minus sine x. Don't forget, it may, look at the bounds, it may not converge. So the next thing we are going to do is just simply use integration by part. Now, we are going to let our u, we'll let u be equal to error function minus 1. That implies du will be what? 2 over square root of pi e to the negative x squared. And how did I get this? It's from the definition I wrote there before. Now, if the v equals sine x, therefore v equals minus cosine x. So applying the error of the integration by parts rule states integral u dv equals uv minus integral v du. So we are going to get this equals uv is this minus cos x times the error function of x minus 1, all evaluated at 0 and infinity. Are we together? And v du, these are v, these are du, plus 2 over square root of pi, the integral from 0 to infinity e to the negative x squared cos x dx. Very straightforward, nothing too difficult. Now, looking at this, I'm very sure we're familiar with how to deal with bounds. The next thing to do from here is just to plug in the limits. We all know cos infinity is surely going to be infinity. Why cos? Error function evaluated at infinity is 1. But we have to give a proof that this thing tends to 1, that this particular bounds equals 1. Now let's leave this part. Let's call this part this. Now let's look at this. Now let's take the question as this. This part of the question is simply cos infinity, error function at infinity minus 1 plus cos 0, error function 0 minus 1. This, by definition, error function evaluated at infinity, by definition, is simply 1. Are you with me? So 1 minus 1 is 0. Cos infinity is what? Infinity. But 0 times infinity is what we call indeterminate form. So we'd have to use limits to prove this thing equals 1. Now, cos 0 is 1. Error function evaluated at 0 is 0. So this is going to give us 0 minus 1, which is minus 1. So we would have 1 times minus 1, which is minus 1. Oh, so sorry. So this should give us 0. Now, let's look at it. Now, this part, we all know See, let me just give a brief proof that this will equal 0. We all know this is the boundary for cos x. I'm going to use the squeeze theorem. We all know this. Yes. So if I multiply both the inequality by error function of x minus 1, I would have error function of x minus 1, error function of x minus 1 cos x, error function of x minus 1. We all know by squeeze theorem or sandwich theorem that if the limits of this and this are equal, therefore it's surely going to be equal to the limit of this. Are we together? So now, if I take the limit as x approaches infinity here, we all know error function evaluated at infinity is 1. 1 minus 1 is what? 0. Error function evaluated at infinity, it is 1. 1 minus 1 is 0. Since the limits are zeros, therefore this thing, so therefore the limit as x approaches infinity in error function is surely going to be equal to 0. Therefore this part of this integral is simply 0. And this part of this is just 1 minus 1, sorry. So we have this equals minus 1 plus 2 over square root of pi, this. So we just have to evaluate this. When we are done evaluating this, then we'll plug it back here and we are done. Now, big psi equals integral from 0 to infinity e to the negative x squared cos x. The only way I can approach this, so we have other ways we can use complex analysis and things like that. But what I'm going to do is I'm going to take the real part. We all know this equals plus I sine x. We all know this. So it is very obvious that the real part of this is this, and the imaginary part of this is just simply this. So that is going to make our work more easy. So this is simply equal to the real part of this integral e to the ix dx. Are we together? On simplification, we should have this. Are we there? On simplification, when we do normal indices law, we will get this. So like I cleaned the board, so that's why we are here. So from where we stopped, now we have this equals to the real part of this. Now we all know before this integral must converge, we have to like e must be raised to power a negative quantity. So that is why I factorized out the negative sign and I made it this way. Now we are all let me not say we are all familiar. Let me not say we are all familiar, you get. So the next thing we have to do is we have to use what we call completing the squares to factor this into this. Are we together? I simply factored this into this using completing the square. So now the next thing, looking at this does not have any x. I can bring it outside and we'll deal with this. Very straightforward. So this is just equal to the real part of e raised to power minus 1 over 4, the integral from 0 to infinity e to the x minus I over 2 squared dx. The next thing is just simply let t or one other variable equals this. If I let t equals x minus I over 2, this implies dt equals dx. As simple as that. So this integral will simply be the real part of e raised to power minus 1 over 4. Sorry. 0 to infinity e to the negative t squared dt. Sorry, the lower part will change because we did a change in variable. Now, if I plug infinity, actually it's still going to be infinity. If I plug 0, we are going to have minus I over 2 dt. Are we together? So we just have to break this integral into two parts and have something that looks related to this. Sorry. I can break it this way. The integral will go from 0 minus I over 2 e to the negative t squared dt plus the integral from 0 to infinity e to the negative t squared dt. What I did here is very straightforward. We all know this a to b f of x dx. We all know is equal to a to c f of x plus c to b f of x dx. We all know this, where c is inside the interval. We all know that. So, by definition, are you with me? This is simply the error function, or this integral. We are familiar. This is what we call the Gaussian integral. It evaluates to square root of pi over 2. Are we together? So we have e to the negative pi over 4. The real part of, now this is also the definition of the error function. So this is simply minus error function evaluated at minus I over 2. This is what we call square root of pi over 2. Are we together? So this is just going to be imaginary. This is what we call the imaginary of error function. Are you with me? And we all know we are talking about the real part. So the real part of this is simply this. So this is just equal to e to the negative 1 over 4 square root of pi over 2. So this simply implies this equals e raised to power minus 1 over 4 square root of pi over 2. Now, we all know the integral we were solving earlier on was simply minus 1 plus 2 over square root of pi of this. But this is simply this. So this is equal to minus 1 plus 2 over square root of pi, square root of pi over 2, 1 over the fourth root of e. This we cancel this we cancel this. We should be left with 1 over the fourth root of e minus 1. So this is our final answer. Thank you for staying with me. Shout out to all my subscribers. Shout out to John. Shout out to Sylvia. Shout out to all of you. Thank you guys. We'll see you in our next class.